Alright, so you are welcome to the part B of this physics video course. We are still on magnetism, right? So I've gone through a lot in putting this together for you. So please, I want you to watch it. This is the second time I work on it. That's why you see all these things like that kind of rough. I recorded a 1 hour video teaching this same stuff, and I discovered after playing it that my mic had fault. I don't know what happened. It was making it one kind of like the sound was somehow. I just told myself that I'm going to leave it like that, but then you guys will not really enjoy the video due to the sound quality. So I had to start all over again. So please appreciate it by making sure everything in this video enters your head. Okay, so this is the part 2 of this video because the part B actually. The first time we talk about the basics. Okay, so if we talk about this, we'll also talk about questions so that when you go out there, questions will not be a problem. So we are going to move straight into business. So we are talking about the concept of magnetic field and all these things on the board. So we are going to follow this order, and then I'm going to try my best to be fast and effective at the same time. So let's go. So what is a magnetic field? What is a magnetic field? That's one of the questions. That's one of the first things there. So please take note that a magnetic field is a region where the effect of a magnetic force can be felt or detected. That's just the basic definition of what a magnetic field. A magnetic field is just like a region where a magnetic force can be felt or please take note, it is a force field. It is a force field and it is a vector quantity. Okay, it is a force field and it is a vector quantity. Alright, so next one to talk about now is the magnetic field intensity. I've heard about this. What am I doing? Talk about this. Let's talk about magnetic field intensity. So magnetic field, for force fields, we have two types of fields. We have the contact field and we have force fields. Gravitational field, magnetic field, electric field, and that force field. Okay. Now, when it comes to force fields, they all have intensity. Like we have gravitational field intensity, we have electrical field intensity, and we have magnetic field intensity. So magnetic field intensity is the force felt by a unit end pole placed in a magnetic field. All these definitions, you don't have to count them. If you understand how force fields works, you discover that most times field intensity is always force over area. Okay, force over, sorry, if it's electrical, force in moving a unit charge, gravitational force in moving a unit mass. Yes, so this one is force in moving a unit not. Okay, so that's just it. The next one talk about this is magnetic lines of force. Okay, magnetic what? Lines of force. And also there's something I forgot to state about magnetic fields. Okay, so actually in the magnets, for example, this is a magnet. This is North Pole, South Pole. Please take note that this place they are called the poles, right? While this area they are called, like, they are actually the field around the magnet. Please take note that magnetic force is stronger at the poles and weaker as we move away from the poles. So the magnetic force is stronger at the poles and then gets weaker. So if you ask a question, in which of the following regions will the magnetic field be stronger, please take note this around the magnetic poles. Okay, so let's go to the next thing I want to talk about. This is what magnetic lines of force. Okay, magnetic. At any point, if you want to write anything, please just take the video back a bit and make sure you are writing. Make sure you have the writing material. This is not movie. Don't just watch the video like that. You learn the videos. Okay. So the next one to talk about is magnetic lines of force. magnetic lines of force actually show the direction a magnetic field is pointing. You understand? They actually show the direction the magnetic field is pointing. Okay, so uh, magnetic lines of force, magnetic lines of force. They're actually imaginary lines. Okay, they're not really, they are not existent. They are imaginary lines that show the direction of a magnetic field. Okay. Please also take note that magnetic line of force, magnetic line of force rather, begins from north poles and end up in south poles. Okay, they begin from north poles and end up. All right, so I said magnetic intensity. Sorry, magnetic line of force begins from north poles and end up in south poles, right? Okay, and please take note that also magnetic lines of force moves out of, let me highlight that, out of north poles and moves into south poles. Okay, and please take note they are imaginary. You can also say magnetic. Let's leave that. Let me not complicate this. I'll just make everything. So, for example, this is a magnet. Okay? This is the north pole. This is the south pole. So, have you seen lines like this before? Like this, like this, like this. See, then you have something like this also. Okay, like moving out of north poles. Hope you can see. So all these lines, they actually what called magnetic lines of force. And what you have to know is that they are imaginary, so they don't really exist. That's why when you put two magnets together, they are trying to attract or repel them. You don't see lines everywhere. Okay, these lines they're actually imaginary. Okay. I said they show the direction of a magnetic field. Yeah, this direction they are pointing. Magnetic line of force will begin from north pole. Actually, if you have let's say uh, two, okay, let me say something like this: north, south, north, south. You will discover that, well, we'll do all these things. Let me not just go. It's not be faster than the pace we actually ought to. We actually begin from north pole and end in south. So we see that I won't start talking about neutral point and everything. Okay, so my line of force, they actually move out of north pole. As you can see, the direction they split that they move out of north pole and they move just something like this. They move out of north poles and they move into south poles. Okay, this is a very good explanation. Sorry, I just had to throw this thing into what I was doing. Okay, so that's it. Then let's talk about the next thing before we talk. Um, we go into details when it comes to magnetic line of force. The next one to talk about here is the magnetic flux. So please take note. Magnetic flux is defined as magnetic lines of force from the same source. You get, so one I've erased the permanent I drew rather. See, if you look at it, one of those lines, call it magnetic line of force. Let's go again. Let me use, I can look as if here just not every time. Don't mind my diagram. um, story as a wrong direction, moving towards south poles. Okay, moving to south poles. Get. So each of this line is called the magnetic line of force. Everything together we call it magnetic flux because they are from the same source, or they are coming into the same source, the same destination rather. So one is called what? Magnetic line of force. All of them they are called what? Magnetic flux. You understand? And please take note that the unit of, let me come here. I'm going to erase this magnet with the lens of force because I will need it. So please take note. The unit of magnetic flux is the Weber, given as this, or we also have um what is it called? We have, okay, yeah, it's Weber. It's Weber. The other one is not really valid. You know, did you get what you guys don't need at this point? Okay, so the unit of the magnetic flux is Weber. And remember, magnetic flux is actually what? Magnetic lines from the same um, points or the same source. Okay. The last one to talk about is that magnetic force, or is more, or we can say the magnetic field is stronger around regions where the magnetic field or magnetic lines of force are closer. If you understand, this also applies not just in magnetic field, even in electric field. Okay, the closer the magnetic line of force or electric line of force, the more stronger the field there or the magnetic force there. For instance, let's see, I don't know if you can see this part of the board. Okay, let's say we have two instances. These are uh, magnetic lines of force coming from an end pole. Now let's say this is point A. Everything here is point A. Okay. I actually see this. Let me adjust my camera a bit. Okay. So if you look at this part, you observe that this part, the magnetic line of force, they actually closer. As the distance in between each magnetic line of force is small. So in this point, we'll say we have greater magnetic field here. You understand? Comparing to this other place where they are spaced. You understand? So imagine this stuff. Let's say it was a complete stuff like the way you see it in the most prepared zones. Let's say you had a complete stuff like this. And we can now say, you can look at this, the magnetic line of force, they actually more at the poles. So that's why magnetic force or magnetic field is stronger around the poles than around the other parts of the magnet. Just as I explained before. Okay, please have that in mind. So the next thing we want to talk about is the magnetic flux density. So I have to erase everything. Any point, if you need to go back to the video on YouTube, so you can just easily take the video back a bit to suit your learning um, frame or learning period. Okay? That's everybody can very fast. So let's go to talk about now is magnetic flux density. Okay. So when you hear density in physics, density is just like length mass language, something over a unit of length. How would I put it? You can say, look at density on its own. Density on its own now is mass over volume. Volume is um, meter cube, right? Density. This magnetic density now is magnetic flux. And please take note, I forgot to indicate magnetic flux. Magnetic flux. Okay. No, my baby said when magnetic lines of force they are from the same source. It says magnetic flux. Okay. So magnetic flux, the symbol is what? is field. You get that's the thing. So if you see something like this field, you know that it's magnetic flux. Okay. So magnetic flux density is actually, this is the magnetic flux per unit perpendicular area. Okay, that's what the magnetic flux density is. Magnetic flux density is magnetic flux density is related with B. Okay, so we say B equals to P over area. Do you understand? So where this is what magnetic flux, okay, and this is what area. I remember this is Weber, right? Units, and this is what meter square area. So you can say the units of magnetic flux density is what Weber per meter squared. And I write this like this, Weber per meter squared, or Weber per meter squared. Okay, so that's it. Another unit, other units. Okay, we have the Gauss. The Gauss is what? An old unit of magnetic flux density. You know, if you remember, I wanted to give you one unit of magnetic flux the other time. I say you don't. Maybe you actually just please take note that Maxwell is also another unit for magnetic flux. Okay, Maxwell, another unit magnetic flux. I did not want to give it to you guys, but all this is they are old units. It's not magnetic flux density, magnetic flux itself. Okay, you can write that somewhere. And also please take note that this Gauss, and also please take note that 1 Weber is equal to 10 to the power 8 Maxwell. Okay, all these things, they are not for magnetic flux density. Instead, they are for what? Magnetic flux. So Gauss is equals to 1 Maxwell per centimeter cube. Okay, so Maxwell per centimeter cube is also another unit of what? Magnetic flux. You understand? That's it. Please take note that you know the other side stuff I'm dropping. Please take note also. Also, please take note that another name for magnetic flux density is what? Is magnetic induction. So in a situation they ask you to look for magnetic induction, they actually asking you to look for what? And this is represented with P. They asking you to look for what? Magnetic flux density. Alright, magnetic flux density. Remember, at areas where the lines of force are closer, magnetic line of force are closer, means we have stronger field here, and magnetic density has actually more. Okay, let me draw a magnet, but I want to illustrate something. Okay, remember they will actually move out of north poles. Okay, okay, okay. So here we also have that they are coming like this into that poles. So I said magnetic line of force actually moves to circles. I believe you understand it well now. You don't mind my diagram. Let me indicate the arrow. There's something like this, or something like this. Okay, now look at it. This is magnetic line of force 1, right? Collection magnetic flux. How do you get now? If for example the area from here now, let's say from here to here, the area is 10 meter squared, and let's say the magnetic flux here is 20 Weber. So if they have to look for the magnetic flux density from here to here, it's just to say magnetic flux density is equal to what? Magnetic flux per area. Let's say the magnetic flux is 20 Weber. 20 Weber over what? 10 meters square. So now I have what? Magnetic flux density equals to what? 2 Weber per meter square. So that's how you can run basic calculations there. Alright. So let's move on. We are done with flux density. At any point, there's anything I forgot to state, I'm definitely going to go back in this to explain. Okay. So we're just laying foundations. All these things are going to be very useful when we start solving. When we enter electromagnetic induction, they are going to be so useful. They are going to be very, very, very useful. Alright, so we're going to talk about now neutral points. Neutral points. Okay? Neutral points. Neutral points are points where the resultant magnetic field is 0 and it exists. Basically, the other ways it can exist, that's where you place paramagnets adjacent to each other with the opposite poles instead of like poles. But that's not really, I don't think that's this level of physics. Okay, so the basic one is just that it exists between like poles and specifically north and north poles. Okay, let me show you something. Let's say bring two magnets together. The south is the north pole, it's another one to the north to the south. So this is, we have like, we don't say like poles, mean the same poles, like at the edges of our closure. Okay, if we have south here, we have north here, that's not like, that's not like poles. I remember the basic law of magnetism, that what unlike poles attract while like poles repel. I believe you knew that already. So let's remember now, this thing actually moving out of one, right, as it should be. Okay, pardon my drawing. So also happen here, move out of not pole. Okay, part of the poles. No, this part here is going to be moving towards that as just to indicate it as it should be. Okay. 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 As look at this point now. This middle point. That's actually there's no, because remember the magnetic line of force or the magnetic fields actually help us to understand the direction of the magnetic field or the concentration or how strong the magnetic field around that area is. Right now, if you look at this, they are actually moving out of it. Okay? And look at this area I wrote as X. You can see that there is no line of force there, and so it means the resultant magnetic field at that point is 0. So that's what the neutral point is. Okay, there's sometimes they will give you a diagram. You just put X there, or any part just so that the thing is just kind of scanty. You're not seeing any line of force there in the diagram, and it's very obvious. Just there are questions they've asked like you just ask. The point in between not poles is what? This thing is what? Neutral point. And also, we cannot talk about a neutral point without talking about maximum density point. Okay. Now the maximum density point is always directly opposite the maximum density point is always directly opposite the neutral point. Okay. So now where the opposite? Look at this part. This is maximum density. And when you hear maximum density, we are talking about point of maximum magnetic magnetic field density, or point of maximum magnetic induction. But I told you another name for magnetic field density is induction. Okay, so please take note. You see these areas we have, the line of force they are actually closer here. That's actually closer here. So directly opposite the neutral point, we always have maximum density. Okay, that's it here. I believe this is clear now. Okay, let's move on. Is there anything I forgot to mention? I got this. I remember as I'm going to actually do justice to that. So let's go to the next thing. Okay. So the next part we are going to move on to the next two stuffs on the list. So the first one to start with is Oersted's law. Okay. We have done with the basics when it comes to concept of magnetic field. Okay. Let's go to Oersted's law. This law states that it states that a current carrying wire has a magnetic field around it. Okay, so it means if a wire is carrying current, it also have what? A magnetic field around it. And what is what actually stimulates or what actually brings about this magnetic field around it is due to the influence of the earth, of the external magnetic field of the earth on that current carrying wire. So it means that a wire, as current is flowing in one direction, there's also a magnetic field around it. And what describes the direction of magnetic field is magnetic flux, right? So it means if there's current, there's also a magnetic field around the current carrying conductor or current carrying wire. That's what Oersted's law actually talks about. So it means for a current carrying wire, we have direction of current, okay, which moves, which points towards direction of what? The electric field. Okay, they also have the direction of the magnetic flux. Okay, which points to the direction of what? The magnetic field. I hope you get this. So it means if a wire is carrying current, there is also a magnetic field around it. That's because when electricity is flowing, magnetism is also involved, and then so the earth's magnetic field is now fully induced as an external magnetic force on the current carrying wire, thereby making it to also have a magnetic field around it. Do you understand? So it means if there's current that is pointing towards the direction of the electric field, there's also a magnetic flux that will point towards the direction of what? The magnetic field. So just as current carries electricity or points towards electricity, we can, for example, you carry a naked wire, if you touch it, it will shock you. That's to show you that there is electric force or electricity is flowing through that. That's just I can actually say magnetic flux is the equivalent of current in magnetic field. So since a current carrying wire, as you can see, current carrying wire, so it means there is current, and now see it has a magnetic field around it. It means there's also a magnetic flux, and all of them we have direction. So please take note that the current is always perpendicular. Let me just write in brackets at 90 degrees. So the magnetic flux. Okay, so with this is actually a cheat. So it means if you're able to understand the direction of the current in a current carrying wire, you'll be able to fully understand the direction of the magnetic flux in the current carrying wire also. For instance, let's say we have something like this. This is a current carrying wire, okay? So we have the wire something like this. This is one perpendicular at 90 degrees. So this will also be what? Direction of the magnetic field. So please, this is current. If you see B, maybe we're talking about magnetic flux. Okay? Alright, so that's it. Magnetic density actually. But let's use B. So this is what Oersted's law states. And then it's actually not complete that way. That's why Ampere now came up with what? The Ampere's right hand grip rule, or it's also called the clenched fist rule. Okay, Ampere's right hand grip rule, also called what? The clenched fist rule. Now what this law explains that if a current carrying wire is held with the right hand and the thumb pointing towards the direction of current. Wait, if the current carry wire is held with the right hand and the thumb okay, with the thumb pointing towards the direction of current, then the four cord fingers point towards the direction of the magnetic flux. Okay, so just put this down. I'm going to explain the principle behind this. Okay, I have the wire here. Let me just get my wire. No, I actually used this is my Apple cord. Okay, look at it now. This is current carrying wire. Let's assume. Hope you can see, because this is a right hand flux, so I'm going to use my right hand. Okay, hope you can see this wire, right? Let's assume I'm holding it now. Let's say with the thumb pointing towards the direction of current. So let's assume the current is towards get the knot or upwards. You see, I have curled my four fingers back, so it means the magnetic flux is pointing towards direction. You understand? So if you look at this, this is actually perpendicular. So the direction of the magnetic flux is perpendicular to the direction of the current. That's just the rule. If you also bend it, let's bend it this way. You can see that the current is pointing downwards. And then see my four fingers, they are pointing towards my right hand direction. Do you understand? Let's present this in diagram, because that's what they're not going to give you live wire example. I did let's say Emeka take this wire, identify without there's no current flowing here, so that's what I just did some assumption. So for the first time we did, I'll come and do it again. When the direction of the current was pointing, when it was towards the top, you can see. So I can say this is the direction of current, and this is the direction of the magnetic flux. Because look at it, towards this side, current is like this. That's this. Our magnetic flux is coming towards this way. That's what we have here. So also, if we have the current pointing downwards, sorry, like this. Which direction will we have the magnetic flux? For example, let me particularize that one. Look at it now. Let me turn for you to see now. So it means if the current is pointing downwards, the magnetic flux was towards my right hand side. Okay, or let me just fix the board. Let's see how to do it. See, this is so magnetic flux is towards this way. No, it cannot be the same direction. Let me do it again. I'm not doing this thing well. Okay. A magnetic flux is towards this way. Let's do that. That means we have to correct that one. Okay. Let's look for this one again. Let's look for this one. We cannot the same direction. Okay, let's go to the wire format. I really think it's giving a little issue, but that's why it should be actually. Let me draw the diagram well. For instance, this side I will give to you example. You see something like this, showing as a wire, and then see current pointing towards. So we ask you, what direction should the magnetic flux be pointing towards? Is it towards this right direction, or is it towards this direction? I will adjust like this. That's when that is going. So one thing I want you guys to understand is that the motion or the direction will actually follow the clock direction. If this is a clock now, this is 12, 6, 3, and 9. This direction is this our clock? This is what clockwise, and this is what anti-clockwise. Okay. So please take note, when the direction of the current is pointing upwards, it takes an anti-clockwise movement. So this is correct. You get, when the direction of the current is pointing upwards, see, takes and anti-clockwise direction. That's the magnetic flux. So these lines, forget my dotted lines, but I believe you get the concept. So when the when the current is flowing upwards, so this is the direction of what the magnetic flux. Okay, then when it's flowing, so that is correct. This one is wrong. Okay, so when it's flowing upwards, current upwards, so we have anti-clockwise direction of magnetic what? Flux. That's for the current carrying wire. Okay, then when we have the current pointing towards the downwards actually, we will now have what? A clockwise movement. Okay. So when we have downward current, we now have what? Clockwise. Alright, so my iPhone ran out of storage, so I had to iterate this self. So let's continue. I said if the current is flowing downwards, we have clockwise direction of what? Magnetic flux. For example, let's do what this guy is. It's really turn this thing. I don't know why it's not. Okay, I'm facing you guys now, right? Which direction is it coming to? This side. Okay, that's this side. Now I've gotten it. It's because of the camera. The top is just because whatever I do now is the opposite that you see. Okay, so that's just it. So downward arrow points the direction of the magnetic flux will be what? Clockwise. That's the way clock moves. But if the arrow is upwards, it will be what? Anti-clockwise. So they can give you diagrams and they ask you if a current but just know the concept. We'll do questions actually, so we'll see how it works. So we see that's what the amperes right hand group helps us to understand that as Oersted has said, that whenever we have a current carrying wire, there is magnetism around it. Now that I've known that, we now see that the direction can be gotten from ampere's right angle rule. So let's talk about the next rule. The next rule actually I'm writing next rule. So the next one to talk about is what? The Maxwell's law. And this law states that if a corkscrew is screwed in the direction of current, it rotates in the direction of the magnetic flux. Actually, for O level, there are no deep questions, or they don't really touch this aspect of this. Okay, so that's just it. So I believe at this point now you understand everything about Oersted's law, ampere's right hand rule, and then the Maxwell's rule. Okay, so we want to continue from the magnetic elements of the earth. That's the main deal here. Okay, magnetic elements of the earth. I don't know, my mic is just kind of giving me little issues. This man that sold this thing for me, I'll just go and return it. Alright, so magnetic elements of the earth. So please take note. You can actually define them as they are what? Properties or elements that helps us to understand the magnitude and direction of the Earth's speed at any place. Okay, and they are actually three. They include 1, We are going to talk about angle of declination, or which is also called angle of variation. 2, we are going to talk about angle of dip, so angle of inclination. And 3, we are going to talk about what? The horizontal components of the Earth's resultant magnetic. Alright, so these are the 3 magnetic elements of the Earth. So I'm going to go into details to explain everything thoroughly. So at this point, I want you to really follow me closely, because if you don't follow me, it will be hard for you to understand. So I believe you are done. Let me wipe it. I need the top of the board for a diagram I want to draw. I want to just draw it permanently. Or maybe if I will use it, I would have used it to explain a lot of things. Okay. We know the Earth is spherical. I know all this geography better. You guys see. We want to argue that the Earth is geodic shape. Whatever the shape is, that's none of my business at this point. Okay. That's the shape is not making us the point. So assuming this is the sphere of the Earth. Okay. No, normally this is northern hemisphere, or the north, and here's the south, right? That's the normal stuff. No, now the reason why magnetism can be felt on the Earth is because, I talk about induced magnetism. Okay, it's because the Earth actually induces magnetism, gets on magnetic materials within the Earth. So actually, science has it that there is an imaginary bar magnet, okay, situated at the center of the Earth. That's the science. That's what science told us. And remember, this is actually what the geographical north pole of the Earth, and this is what the geographical south pole. Right? So science has it that there's an imaginary bar magnet situated at the center of the Earth, and then you see something, and then you now tell us that the south pole is towards. So since there is an imaginary bar magnet, and then you know that a magnet will always stay. The only reason this magnet is still here and not fall and hit our head on this Earth is because there is something that is attracting it here, that is holding it. Also, same thing here. So with that assumption, that shows that we also have the magnetic north pole. Magnetic north pole situated along this path. No, north and south will actually attract, right? Then also have what? The magnetic south pole at this path. So this will not attract it. So that's the assumption. So that means that towards the northern part, we have both the geographical north pole and the magnetic north pole, and we have the magnetic south pole here and the geographical south pole. So it means that the magnetic and the geographical south pole, they are towards the south, while the magnetic and geographical north pole, they are towards the north. I believe you are following. Okay. Now, yes, normally in a magnet, for example, this is a magnet. Any line that passes through the magnet that runs from the north to the south pole, or that splits the magnet into two, we call it either the magnetic meridian or the magnetic axis. Please, English should not confuse you. Sometimes you want to explain anything, but that doesn't even make it to even score. That they will not ask you any question and ask you which of the following is correct. Hey, might know. Just put it that way. And also for the Earth, also, this is, for example, this is north pole of the Earth, this south pole. There's also a line that runs through from the north to the south pole that divides into two spheres. I can call it the geographical meridian, or we can say the geographical axis. Okay. So if you are to bring this knowledge here, it means assuming, okay, let's shorten the width of this magnet so I cannot be in the center like that. So assuming this is the center of this line is running through the Earth. we can call this what? This broken line our geographical what? Meridian, right? And then through this magnet, we can call the one that runs through it the what? Magnetic meridian. So as you can see, we now have two meridians. As what we just did is that we brought this knowledge to this part because of this imaginary bar magnet, right? So you can see we now have two meridians. We have the geographical meridian, which is the line that runs from the north pole of the earth to the south pole, and we also have the magnetic meridian, which runs through the bar magnet. And remember, I said the theoretical reasons why it's assuming that this bar magnet has not, because if it's at the center of the earth, if there's nothing that is attracting it, if I love for break everybody head for it, you get scatter everybody head. But then the reason why it is staying there unhindered or unshaken is because there's a strong magnetic attraction. Because if this is the north pole, it is taking that the north pole of the imaginary bar magnet is close to the south pole of the earth. Okay, this is the north now, right? It's towards the south for attraction. Why the south is towards the north? Okay, that's it. So now this knowledge. Now the question is, how does this knowledge help us? It helps us because we want to talk about what? The angle of declination. Now the reason we are saying this way is because, okay, let me point another scenario just so you can see this part of the board. For example, look at this structure also. Let's say because this bar magnet can be like this. What's the center of the earth? You don't actually mean one vertical, and be like this. Okay, let's say this will be the south pole, this will be the north pole, but this actually stick towards the northern part. Okay, so any line that runs through it is going to be what? The magnetic meridian. And remember, this is going to be what? The south pole, geographical south pole, and this is going to be the geographical north pole. There will also be a line that will run through this. That's the what? Geographical meridian, right? Now, if you now observe something, you see that there is an angle in between the magnetic meridian and the geographical meridian. It is this angle that is called the angle of declination. Okay, so if you are to define angle of declination, we can say, let me define it properly here. Angle of declination is the angle between the geographical and magnetic meridian, or as it's very concise. Hope you get it now. So the angle between, now the reason why we're not having the angle of declination here is because, please take note that at the north pole, you see this magnet, you see they're actually kind of coinciding, like the geographical meridian and the magnetic meridian, they are very close. There's no angle between them. So, and then please take note that the angle of declination is always 0 at the geographical north pole, and this is the geographical north pole. So at this point, when it's like this, there is no angle of declination. The reason why we have angle of declination is when the bar magnet is not straight. And the question is, why is it that that's how it is in some part of the earth at different times? Do you understand? So please think that the angle of declination is always 0 at the geographical north pole. Alright, there's something I want to explain now. Okay, I want to explain something differently. Okay, so let's recap. Angle of declination is the angle between the geographical and magnetic meridians, or as is. Please take note that it is measured with an instrument called the declinometer. An instrument called what? the declinometer. That's the instrument that is used to measure what the angle of declination. You grab. And also please remember that the angle of declination is always zero at the geographical north pole. Okay. Then next one to talk about is that where will I use now? Okay, let's use here. Okay, he's taking that lines of equal angle of declination are said to be isogonic. Okay, lines of equal angle of declination are said to be isogonic, and also lines of zero angle of declination are said to be what? Agonic. Is taken. So we can say the Earth is agonic at the geographical north pole. You get it? I said lines of what? Zero angle of declination are said to be agonic. And then remember I said the angle of declination at the geographical north pole is 0. Do you understand the logic now? Okay, right. So the next thing is that let's understand something. Please take note that mariners and those guys that travel on the those pilots, they make use of this knowledge because they use what we call the magnetic compass. In the next, I'm going to explain what the magnetic compass is and how it works. Okay, are you ready? All right, so let's talk about something else now. We're going to talk about the method or how the magnetic compass works. Remember, magnetic compass is used for navigation. Okay, it's used for air navigation and sea navigation. And remember I said on the compass the line that points to the direction of the ship or of the aircraft is called the Luba line. Remember I actually said that when I was explaining angle of what? Declination or variation. Okay, now I also I was saying something that now let's go back to diagrams. Pardon my drawing. Let's say this is the Earth. This has a north pole. We have the north, geographical north. It can be the geographical north or the magnetic north. Here can be what? The geographical south. Or actually, I don't want to write two south poles and two north poles. So imagine, let's say that bar magnet is pointing somewhere like this. Remember, this will be the south because the south pole of the bar magnet is towards the magnetic north, and then this is the north pole towards the magnetic south. Okay. Now remember, there's going to be a line, a magnetic axis or meridian that will cross through it, and also through the Earth there will be a line that will cross. That's the geographical meridian. So this line is called geographical meridian. All right. Then this other line is called what? The magnetic meridian. Now when we have something like this, if you look at it, there's going to be what? This angle here, and that's what we call the what? The angle of what? Declination. Now I was trying to explain something. Let me explain it clearly. Let's say I'm headed towards the north. Okay, let's say I'm going to this point X here, and as you can see, remember the magnetic compass points towards the direction of the magnetic north pole. Please take notes. The magnetic compass, let me know to write that. I've said this already. The magnetic compass points the direction of what? The magnetic north pole or the south pole of the bar magnet. Remember, the south pole of this bar magnet is towards the north magnetic pole. That's why it can actually stay without falling off. Okay, so that's it. So remember, if I'm going to this towards direction, we are saying that this bar magnet is not straight. Hope you know I'll be getting a wrong bearing because this thing is not straight. You see, so that's why people that use compasses to travel, they have to study the angle of declination at different places they are going to. So if they are point X, they should know that, let's say, the angle of declination is actually giving us, let's say, north 30 degree west. You see, that's the place. And let's say if their compass now is now telling them north 50 degree west, they should be able to use the value of their compass and the value of the angle of declination of that place to actually know the true bearing of where they are going to. Do you understand? That's how this thing works. So the logic is this: when they are going towards that, because the thing is that you always have knots. Yeah, because the compass points towards what? The south pole of the bar magnet, which is also the magnetic north. So we always have knots here. I don't know if they can change questions for you, Sha, but assume we have knots. This one will not be the issue. The issue is whether here is going to be west or east, because this place can actually be east. The magnetic compass can be giving you a bearing like this, such as east. While it can also give you the such as west. Here can be east also. So it does not matter. The main thing is that there's a logic, there's a way you solve questions like this, okay? Now, if they are the same direction, the same direction, hmm, the same direction, add both values, okay? Add both values. Different direction, different directions, for different directions, subtract both values, and then retain the direction of the greater value. Okay, for example, let's say the bearing of a particular place or the angle of declination. Let's say the angle of declination is given as not 30 degree west or 30 degree west of north, and then the compass is reading not 10 degree west. You see the same direction. Why? West west. What do you do to get the true bearing? True bearing, let me just use it as TB, is equals to what? 30 plus 10, so that's 40. So the true bearing is not 40 degree west or 40 degree west of north. Do you get? Why? The same direction. What if we have east here and we have east here? Same thing. Do you understand? So if they are the same direction, you add. If they are different direction, let's say this is not 30 degree west and this is not 10 degree east, what do? You subtract. It will be 30 minus 10, right? That's 20. Now the question is it not 20 degree west or not 20 degree east? Or do we just guess? There's a way you do it. The way is that after you have done the subtraction, because they are different directions, let your answer take the direction of the greater value. Okay? If you look at it, the one that has west has 30, the one that has this has 10. Between 30 and 10, which one is greater? It is what? Actually what? 30. So 30 will not be what our answer will take. So sorry, the sign of 30 is west. So it will not be not 20 degree west after I have subtracted. So remember the logic, the same direction, add both values, different direction, subtract first, then let your the value you are getting take the sign of or the direction of the greater value. So for example, let's say the angle of declination at the place is not 70 degree east, and let's say the magnetic compass is giving us a bearing of not 20 degree west. What do? We add? No. First of all, they are different directions, west east. So you subtract. To be 70 minus 20, that's 50. So is it 50 degree of east or west? Which one is bigger? That of east. So it will be n 50 degree east, because east value is bigger. So that's the logic behind how the compass works. Okay. So we have not talked about angle of dip. So let's move on. Now we are going to solve questions later. That's just the basic. If you understand, you should understand that. If you don't understand, just kindly take the video back a bit. So we have talked about angle of declination. I have talked so much about it. So let's talk about the next magnetic element, angle of dip or angle of what? Inclination. Please take note the angle of declination is also called angle of variation. Meanwhile, angle of dip is also called what? Angle of inclination. Now it is true that in magnetic material, as we were told from the beginning, that magnetic material has come to rest in the north-south direction, right? North-south. Then if you want to demagnetize it, you put it in the east-west. Hope you remember that. Now the thing is that this thing holds, okay? But then no true magnetic material will rest in the north-south direction without tilting to the horizontal. So it means if it's, now look at, for example, let's say um, let's say um, this is a magnetic material. This is not sat. It's coming to rest. It's just straightforward like this. This is non-magnetic. Okay, that means it's not really magnetic material. A true magnetic material will actually kind of fit. Okay, say north, south, to teeth. So there will not be, and let's say this will be the vertical, right? So this will be the horizontal. So it will actually have an angle of teeth to the horizontal. So that angle of teeth that to the horizontal is called what? The angle of the magnetic material. So if I may ask, what's now angle of dip? Angle of dip or inclination is the angle between the resultant, let me just use the Earth's resultant magnetic field and the horizontal. You grab, that's it. That's what angle of dip is. It's given as phi. You get, that's angle of dip for you. The angle between the Earth's horizontal magnetic field and the horizontal. So please take note that please write it, that the knowledge, oh my ring light actually it's somehow centered around there. Let me block it a bit for you. Okay, just have to look for, I believe you have to play the video now. You have to take it back to hear what I was saying well. Okay, all right. So the angle of dip is the angle between the horizontal Earth magnetic field and the horizontal, you get. So what you have to know is that a true magnetic material can never be like this. So please take note that, write it somewhere, that the knowledge of angle of dip is used to differentiate between a magnetic material and a non-magnetic material. Why? A non-magnetic material will rest horizontally, will rest vertically in a north-south direction without tilting. Do you grab? But a non-magnetic material will never rest in the north-south direction vertically. It will always tilt with either the south pole or the north pole pointing downwards. So either of them can point downwards. And let me tell you how like there's a variation there, or there's a difference there rather. So please take note that in areas above the equator or along the northern hemisphere, the end pole points downwards. Otherwise, when you stay in details with diagrams. And in areas below the equator or along the southern hemisphere, the south pole points downward. And for this one, example of such areas include Egypt, Britain, and England. That's for the first one. Then for the second one, example, Egypt, Nigeria, and Australia. So I'm going to use the diagram to explain this, so you don't have to get confused. Okay, now let's say this is the Earth, and let's say now this is that bar magnet, the limit. Now remember, the midpoint of this actually called the equator. We actually did geography now. We learned about lines of latitude and longitude. So the middle is called the equator, right? So anything above here, this is called, because this is the north, this is south, right? Everything above the equator is, we say it's the northern hemisphere, right? Because this is sphere, and half of the sphere is called the hemisphere, right? So you now say yes, what? The southern hemisphere, right? So if the place where we are talking about now is in the northern hemisphere. It means as this thing, remember we are talking about the fact that the magnet will kind of have an angle of teeth to the horizontal, right? And then you see in this northern hemisphere now, it is the end pole that will point downwards because it's above the equator and it is in normal. As I said, in areas above the equator, that's above the equator, or in the northern hemisphere, the end pole points downwards. That's when it hits. You know, this is the angle of dip that we're talking about. That's the angle between the earth's horizontal magnetic field and the horizontal, the graph. So it is the end pole that will dip or that will point downwards in the northern hemisphere or above the equator. But if it's in the southern hemisphere, if it's in the center hemisphere or below the equator, it is what? The south pole that will hit. An example of something is in Nigeria or Australia. So since you're in Nigeria, if you want to explain, if you want to draw a diagram now to explain to somebody, where will it? Where I want to put it downwards, is it south pole or north pole? It is south pole because you're in the southern hemisphere. And please also take note that angle of dip is 90 degree at the poles and 0 degree at the equator. I don't think there's any question has come out as this in this topic. They ask it every time. So the value of the angle of dip at the poles is 90 degree, while at the equator is 0 degree. Then please take note, the normal value of angle of dip is 70 degree. I'm not saying at the pole or equator now, like the normal value of angle of dip is 70 degree, diagram, while at the poles is 90 degree, at the equator is 0 degree. Please take note that. I also take note that along the equator, remember the what angle of dip is 0 degree. And please take note that there's a state in Nigeria that is situated in the equator, like that the magnetic that this equator passes through, and that state is Jos. Plateau Jos, right? Plateau state rather. I remember I've asked QT questions. I have asked QT students this question before. Plateau is the state, Jos is the city. So if they ask, in which of the following states is the angle of dip 0 in Nigeria? Is it Jos or Plateau? It is what? Plateau state, but the place is Jos. So please take note. They have asked it before in the exam. And also please take note that lines of equal angle of dip, they are said to be isoclinic. Write it somewhere. Lines of equal angle of dip, they are said to be isoclinic, while like lines of 0 angle of dip, they are said to be what? Aclinic. Sorry, agonic is for angle of declination. Please write it. Then please take note the angle of dip is measured using an instrument called the dip cycle. So please take note, angle of dip is measured using an instrument called what? The dip cycle. If they ask you which of the following magnetic elements is used to differentiate between the magnetic material and a non-magnetic material, what's the answer? Angle of dip. Why? In non-magnetic material we just rest vertically in the north-south direction, while magnetic material will be found to tip at a particular angle. Okay, so that's it about angle of inclination or angle of dip. So the next magnetic, remember we listed 3 magnetic elements. We said one angle of inclination or observation, angle of dip or inclination, which we just talked about. So it's mainly the horizontal component of the Earth's magnetic field. So please take note that we have horizontal component, which is the component of the Earth's magnetic force to the horizontal magnetic field rather, to the horizontal, and is represented as H, and then we also have the vertical component of the Earth's magnetic, which is the component of the Earth's magnetic field to be vertical, and it is what represented as V. Please take note, H is equal to B cos B, where B is equal to what? Magnetic flux density, and C is equal to what? Angle of the. All these I'm going to you guys, I think that it might even go and be cramming questions. Meanwhile, they are easy things. Yeah, I remember back then, I saw one question, they gave me angle of B, they said for the horizontal component. I was just doing rubbish because I don't know what to do. It's this simple. So why this V is equal to what? B sin phi, where B is what? Magnetic flux. I want to ask you a question. Answer it before I give the answer. Magnetic flux density is also called what? It's also called what? It's called what? Magnetic induction. One is angle of B. So that's it. So that's just about the horizontal component. So we are done with what? The magnetic element and calculations. The calculations we did is the calculation under angle of declination. Okay, so let's move to the next thing is applications of the Earth's magnetic field. Okay, application of the Earth's magnetic. It's used in the major thing is just navigation. That's just the major thing. And all those mineral exploration, but let me just do navigation. Like for all those navigation of seas, of air and seas. Okay, air by all those pilots, they use compass knowledge. Seas, all those sailors, they use compass knowledge. So next one, talk about the direction of the magnetic field. There are two instruments used to measure or actually detect direction of the magnetic field. Okay, of a magnetic field rather. Right, we have the compass needle, and we have what? Iron fillings. All right, we have compass needle, we have iron fillings. For this compass needle, we use it for what? Weak and sensitive fields. It's used for weak and sensitive fields, e.g. Fields around a bar magnet or two bar magnets. You also use it to measure what? The direction of the what? Earth's field. I'll explain on this thing. Then for iron fillings, it's used for what? Strong and insensitive field, e.g. the poles feed along the, let me say the board, okay, feeds along the poles of bar magnet. Okay, then feeds of a current carrying wire. So remember, the direction of the magnetic field is actually the direction of the magnetic flux, right? That's where lines of force they point towards. So we have two things that you can use to measure it physically. Because remember, I said you cannot see lines of force. So all these two instruments, they actually point as an indicators. They help us to understand the direction of the Earth's magnetic field. So there are two of them. We have compass and we have iron fields. Please take note that the compass is used for weak and sensitive fields. And please take note, it's around the, like fields around the bar magnet or the Earth or around the Earth's field. Please take note, you don't use compass needle to measure the field at a pole, magnetic pole. They have asked questions on it severally to test your knowledge. If you just see pole, edges, I don't know what any English you want to use to present magnetic pole. Like for example, let's say this is a magnet. This is the pole now. All these ones are round, they are the feet. If it's pole matter, just forget it's not compass needle. It's what iron fillings. But if it's around, you use what compass needle. If it's a current carrying wire, you use what iron fillings. Check grab. Iron fillings is for the poles and for current carrying wire. So let's go to the last thing on this list. Oh, second to the last. Let's talk about diamagnetism and paramagnetism and even ferromagnetism. Okay, ferromagnetism is not specific to chemistry. Let's talk about the magnetic materials. So let me define. They are materials, or we can say molecules, that set their feet, or we can say align perpendicularly with the Earth's external magnetic field. You know what I want to see here is perpendicularly. Okay, it is the weakest form. Okay, it's very weak. And also there are magnetic materials. I have to write this now. I'm tired of writing. So let's move. There are magnetic materials have a negative. I want to explain this now. It will take time, and we don't have that time. Have a negative magnetic susceptibility or permeability. That is value less than 1. Okay, so I also explain magnetic material. So the magnetic materials are materials that set their fields or align perpendicularly with the Earth's magnetic field. So if you have a material that is magnetic now, and then its own magnetic field is aligning perpendicularly at 90 degrees to the Earth's horizontal magnetic field, it means it's diamagnetic. I would have gone to explain this, but we don't have that time. Just know it, okay? We don't have that time. This question already finished. So I said it is the weakest of all from that. So if you compare it to paramagnetism and even ferromagnetism, it is weakest. And also it has a negative magnetic susceptibility or permeability. That's the value of the magnetic susceptibility or permeability is less than 1. That's why I said it is what? The weakest. And it is negative. Check that. Just need to don't go down. That's what I can explain, but there's no time. So let's talk about. I don't have to write it in. Assume you have written this one, so let's talk about the next one. I'll just have to edit it here. Let's talk about paramagnetic materials. There are materials or molecules that set their length. Is there anything like parallelly? No. In a parallel direction with the edge external magnetic field. It is stronger. It is stronger than their magnetism. Okay. And let me see here now what paramagnetic have what a positive, just like opposite. They have a positive what magnetic that is greater than 1. So hope you get. So you can just go back to get the difference. The major difference is that they are magnetic. They are what acting parallel. That paramagnetic can be made parallel. You get. Their magnetism is weaker. Paramagnetism is strong. This one has a positive. Sorry, the magnetic first has a negative what magnetic susceptibility or permeability. Why paramagnetic materials they have what a positive magnetic susceptibility or permeability. For the magnetic, their value of magnetic susceptibility is less than 1. For this one is greater than 1. So that's the difference. Let's talk about the last thing here. Oh, keep questions. Okay. let's talk about the last thing here. Let's talk about sintering. Now we have two forms of magnets. Okay, it can be a powdered magnet, or we have also have bar magnet. Okay, now powder magnet, you know how powder is now, they are like in bits. You get bar magnets are the ones like in blocks. So the process of converting powdered magnets to bar magnets through the application of heat and pressure is now what we call sintering. So sintering, if they ask what is sintering, sintering is the process of converting powdered magnets to bar magnets by the application of great heat and pressure. So that's it, guys. So please revise everything we have done, review it, and then watch the videos where we put questions before we move to first on the current carrying wire. That's the motor effect. So let's move.